now, I'd like to introduce the speaker, Bill Goldman, and he will beat my apologies. I'm going to look up your title.
Dynamical systems, the microphone works.
Yes.
Dynamical systems arising from the classification of geometric structures on manifolds.
Thank you very much.
So I'd like to begin by thanking the organizers for the invitation to come here to celebrate the birthdays of Yael, Jonathan, and Lisa, all of whom I've known for a long time. I don't really remember when I first met Yael or Jonathan, but I distinctively remember meeting Lisa in January of 1989 when I was visiting the Maths Institute at Oxford. She was a first-year graduate student at Oxford, and we talked then. I was learning about Higgs bundles and loop groups and Floer homology. But then, coming from much different points of view, our research interests interacted, and in particular, the 1992 paper that Jonathan and Lisa wrote on Bohr-Sommerfeld orbits and the Verlinde formula was very influential in work that I did later on ergodic theory and moduli spaces. And so that's what I'll be talking about today. And I'd like to begin by describing the origin of my interest in this subject. So originally I was going to give a fancy talk with an interactive Mathematica program, which I have, but I wasn't able to get it set up right now, which is probably easier. But I'll just say what I want to get to. If there's some time afterwards, I'll show the program. But in particular, I'd like to advertise a certain dynamical system, which comes from a Poisson structure on R3 that's related to a cubic polynomial. Let me just write it down. Call it K of XYZ. So this is on R3 or C3. And the Poisson structure is given by a bivector field, which is obtained by taking the volume 3 form, 3 vector, and take the inner product with the differential of K. And so this is a fascinating Poisson manifold, and I'd like to advertise it. It's very mysterious, I think, in C3, and I'll mainly discuss the real points, which is sort of the motivation or the destination in this talk. Okay, so by the classification of geometric structures on manifolds, I want to describe a very general problem where we start with a fixed topology sigma, and I want to relate the fixed topology with a geometry. Which will be given in the spirit of Felix Klein and Sophus Lee, the Erlangen program, by a homogeneous space. So we have a space X and a Lie group G, which is acting transitively upon it. And the geometry of this homogeneous space are just the objects on X that are invariant under the transitive action of G. And then around in the 1930s, Erisman proposed generally, how do you put the geometry of X, the G-invariant geometry of X, locally on the geometry, in the topology of sigma. So for example, if we have Euclidean geometry, a structure like that will just be a flat Riemannian metric, and say the two-sphere does not admit such a structure. The two torus does, and have many structures. They all correspond to elliptic curves and quotients of the complex line by a lattice. So this very rich structure, and that's the deformation space. So we might have, I'll call it, let's see, is this visible from the back? Probably can't go much lower though. So we have the deformation space of GX structures on sigma, and that the points of which correspond to equivalence classes of marked GX structures on sigma, the topology. So this is very general. I don't want to say too much about it since I want to get to the dynamical system. But for example, I mentioned Euclidean geometry where X is Euclidean space and G is its group of isometries. X could be the same space, affine space, and G could be its group of affine transformations. And these are the affine structures that we've been hearing about, say in Mark's talk yesterday, where we have a coordinate patches that match by coordinate charts into affine space so that the coordinate changes are local restrictions of affine transformations. I'll say that in a moment. This is very important in the talk. And these kinds of affine structures that I defined are going to be traditionally just flat torsion tree affine connections. And then these structures here are going to be flat Cartan structures or Cartan connections in a very general sense. Or we could have flat projective structures, flat conformal structures. Given any homogeneous space in any topology, we get an interesting problem that involves many different areas of mathematics depending on the different flavors of geometry. Okay. Now, how do you classify them? So, for example, if sigma is the two-sphere and the geometry is Euclidean, there aren't any. That's pretty easy. But then when we have sigma is the two torus and we have Euclidean geometry, we have many flat tori. And so we can look at the space of flat tori, say flat n tori. And these correspond to quotients of Rn by lattices. Okay, now, how do we study a lattice in Rn? Well, a lattice is just the group generated by a basis of Rn. And so we can think of this as being spaces of bases of the vector space Rn modulo some equivalence relation where the equivalence relation corresponds to the change of basis. And the space, what is the space of bases of Rn? We'll just take a basis, line them up as a matrix, and you get a torsor for GLNR. Now, we're interested in isometry classes, so two bases should be equivalent if they're related by an orthogonal transformation. So we quotient by the orthogonal group, but then we also have to look at the equivalence relation of change of basis. This is the marking. The marking of the lattice is the basis. So a marked lattice is a basis. And so that corresponds to the biquotient by GLN Z. That corresponds to the change of basis. Okay, well, that's nice. We have a space, and it has all kinds of interesting geometry on it itself. Another example, which is a little bit different but very familiar, is if we want to look at the classification of Riemann surfaces. So we might have M will be a Riemann surface. There's the Riemann moduli space, which is a nice classifying space, a deformation space of moduli space of Riemann of curves, but it's fairly complicated. It's not a manifold. It's still a nice quasi-projective variety, but it's efficiently studied in terms of the Teichmüller space. And a Teichmüller space consists of a marked Riemann surface. So we have a marking, which is like a topological coordinate system. And when I say topological coordinate system, I mean we might have M will be a GX manifold or a Riemann surface, and M prime might be another. We say that two marked Riemann surfaces are equivalent if there's an isomorphism, either by homomorphism of Riemann surfaces or an isomorphism of Arrhenius structures. So this diagram commutes up to homotopy. Okay, and so that's what a marking is. It's this labeling. So remember, sigma's topology and M is geometry. And the space of equivalence classes of marked Riemann surfaces is the Teichmüller space. And then, so the Teichmüller space is a nice complex manifold, and the change of markings correspond to mappings. Now, turning this diagram around a little bit, from sigma to sigma, these will be now, say, homomorphisms, or they'll be characterized by the analog of GLNZ, the change of basis. The change of topological basis here would be the mapping class group. The mapping class group. Okay, now the mapping class group is a very important group. It's sort of the structure group of low-dimensional topology. And the key point is that the mapping class group acts properly on the Teichmüller space. In the same way that GLNZ acts properly on the homogeneous space, the symmetric space of GLNR. Okay, and so the classification in both cases is given by a nice deformation space with a proper action, and we can look at the quotient moduli space. But in general, the mapping class group of sigma does not act properly on the deformation space. And so that's what I'd like to talk about today. In particular, the deformation space will be given by this Poisson manifold. In many cases, it'll be this family of cubic surfaces in R3, and the mapping class group here, well, with sigma. So G will be SL2. I'll eventually go down to the real points, but let me just start with SL2C. We'll just call it SL2. And sigma, in this case, will be the one-hole torus. And the mapping class group of sigma is the modular group. Well, it'll be PGL2, it'll be GL2Z. In a little while, I will extend this to get more symmetries, but the dynamical system I want to advertise is an action of the modular group on R3. Okay. So now Riemann surfaces are not really Ehresmann structures in this sense. If they were, you could prove that the two-sphere doesn't have a complex structure, which we know it does. And that's because we need to require that the coordinate changes are restrictions of globally defined automorphisms. And any coordinate atlas for the Riemann surface P1 has to involve analytic functions that are not just analytic biholomorphisms of C that have to have some have to have poles. Okay, so this example of Teichmüller space is not really a GX structure in the sense of Ehresmann and Thurston, but it's analogous. However, and there is the uniformization theorem, which is very powerful and non-trivial theorem, which asserts that the category of Riemann surface is the category of certain Riemannian homogeneous structures. And in particular, if the Euler characteristic of sigma is negative, so sigma is a surface of genus greater than 1, if it's orientable, then the Teichmüller space of sigma identifies with the deformation space of hyperbolic structures on sigma. Okay, so it's been customary, but I think erroneous, to call the deformation space of hyperbolic structures on sigma Teichmüller space. It really should be called Fricka space, and then this deep theorem of Koba and Poincaré asserts that there's an isomorphism between Teichmüller space and Fricka space. In that case, one does have, Teichmüller theory does fit into this deformation of locally homogeneous geometric structures. And in particular, the mapping class group of sigma acts properly on these spaces, on the Fricka space. So I don't know if this is good news or bad news. If you want functions on the quotient and you want a nice quotient, if you're a function theorist, it's good news. And there's a lot of rich theory on the geometry of the Riemann moduli space. But if you're a dynamicist, then the dynamical system is completely trivial. So it's dynamically interesting because it's dynamically uninteresting, but function theoretically nice. Most of the time, the dynamics is very complicated, and that's what I'll be describing. Okay. So, in particular, one sees in this family of examples, the both trivial proper dynamics as well as chaotic dynamics, and that's what I want to describe in this talk. Okay, so I should maybe mention something else. Another theme will be that when we have these structures, it's useful to put in singularities sometimes. And so we can imagine putting in, say, to a Riemann surface, branch points or cone points. And then this leads to an interesting theory. And we'll see that, at least in the case I'm describing, that we do get proper actions when we put in some isolated singularities. So, in particular, the theory of Teichmüller dynamics and translation surfaces corresponds to GX structures where X is the plane R2, G is the group of translations, but we allow singularities that are cone angles of multiples of 2 pi. And that's equivalent to the theory of Riemann surfaces together with non-zero abelian differential. So this is a thriving subject, closely related to the mapping class group as well. Okay. So there's a nice paradigm. This is a theorem which was first noticed in this generality by Bill Thurston. One of these structures is given by a developing map. You take the universal cover and then extend the coordinate charts by analytic continuation to give a map, a multi-valued map, which means a map defined on the universal cover, into X. The deck transformations are then the composition of the coordinate changes. And here it's important that the coordinate changes are restrictions of globally defined mappings of X. Okay? That's why these Riemann surfaces don't qualify as Ehresmann structures. But you then get this globally defined construction starting from a coordinate chart. As you apply a deck transformation, you get a composition of the local maps, and that deck transformation is realized by an element of G, a single element of G. That defines that's a holonomy, which is a homomorphism from the fundamental group, which I'll call pi, into G. And there are choices in constructing the developing map, but if you remove those choices, then you get a map into the quotient by automorphism. So here G is acting by composition on one side, the inner automorphism, and we have this space. So this is in general not a very nice space. Pretty much any kind of pathology can arise in full generality. If G is a real algebraic group, then this is a real algebraic set. That's fine. It might not be a manifold. It may have singularities. G will be acting algebraically, but it may not act properly or freely. So the space will have some singularities. It may not be Hausdorff. However, we may want to take its GIT quotient. That'll be called the character variety, since the functions are characters. That's a pretty good approximation for the applications I'm describing. That's what I'll be talking about. But even though this space is somewhat it can be pathological, Thurston proved, and sometimes this is called Ehresmann-Thurston. Ehresmann's point of view is very important here, And I would probably add Andre Weil, who proved a special case of this. And the principle is that basically this map is trying to be a local homeomorphism. So we have to, you can define a natural topology on this space for which this is a local homeomorphism under certain cases. Okay. Now, in particular, the space of equivalence classes of homomorphisms from the fundamental group into G can be identified with the space of gauge equivalence classes of flat connections. And so, in the case of in the case pi is the fundamental, in case sigma is a surface, then a closed surface, there's a natural symplectic structure that's invariant under the mapping class group. And I should mention that the mapping class group, again, there are some technicalities, but in general, this maps into the outer automorphism group of the fundamental group. Because we have quotienting by inner automorphisms of G, the outer automorphism group of pi acts on the quotient, and this is equivariant with respect to that. And so when sigma has boundary, like the puncture torus, then there's the peripheral structure defines a natural Poisson structure, which is the one that I'll be describing. Okay, and so the theory of the space of flat connections in its moduli space then can be thought of as local structures on the deformation space of Ehresmann structures. Okay, are there any questions? This is sort of the end of the general discussion, and I'd like to now move to the special case of the one-hole torus. Now, there are various reasons for looking at the one-hole torus. In some sense, the character variety for the one-hole torus is a building block for the character variety in general, because every surface can be decomposed. So here's a genus 2 surface. It can be decomposed as union of two one-hole tori in this way. Yes.
I mean, for the closed torus, I can see that the modular group is here. But why for the one-hole torus? How do you define the modular group exactly?
Let's see. Yeah, that's a good question, which I. Yeah, there are various. I think I want to assume that these are homeomorphisms that are pointwise the identity on the boundary. But that's different than if you say just assume that it's on the boundary. And I also want to, usually the mapping class group refers to an orientation preserving homeomorphism. I want to relax that to allow orientation reversing homeomorphisms. But in general, say if you have a more complicated surface, you'll have one-hole tori and four-hole spheres. That's the four-hole spheres. Is this a four-hole sphere? But the four-hole sphere is also quite a fascinating object. Its relative character varieties are also described by a family of cubic equations. I won't have time to describe that, but this is quite interesting, and the cubic equations that come in, the theory of the cubics, which is what I wanted to show with the computer demonstration, is seem to be intricately connected to the dynamics of the action. Okay. Well, let's see, how much time do Do I have to? 21, good. Okay, so what is the fundamental group of the one-hole torus? So we have two simple closed curves. We call them X and Y. And the fundamental group is the two-generator free group generated by X and Y. Okay. What's a homomorphism? Well, a homomorphism from pi into G is determined by what it does on the free generators. So corresponding to what X goes, it's G, just pairs of elements of G. And what's the action of G, the equivalence relation? Well, that's just simultaneous conjugation. So we just have inner automorphism applied to the X coordinate and the Y coordinate. Okay, so that's the quotient space on pi G. Okay. Now, and then, well, I want to make life a little bit more complicated and introduce two more generators to the fundamental group. So I want to give a redundant presentation that's related to the geometry. So I have X, Y, Z, and K. And Z will be the inverse of the product of X and X, Y. Now, you may recognize this is the relation for a pair of pants or a three-hole sphere where the boundary components correspond to based loops once you make some choices whose define the relations for another redundant presentation of three-hole sphere, of the three-hole sphere, the fundamental group of the three-hole sphere. And in particular, the three-hole sphere and sigma, the one-hole torus, are homotopy equivalent. They both can be retracted down to a spine. So say the spine here would just be the union of the red curves and the red curve and the green curve. Here you take the red Y curve and the green X curve. Okay, so I'll come back to that remark later. And then K will correspond to the boundary. And that's the commutator of X and Y, which will be X, Y, X inverse, Y inverse. Okay. So that's the redundant presentation I want to use for the fundamental group. And now there's this marvelous theorem about the character variety, which is, I think the earliest reference I know for this is a paper of Vogt from 1889. Which is basically the statement that the quotient, now I'm going to take the GIT quotient. So Hom pi G is just SL2 cross SL2. G is acting by diagonal conjugation, but that's isomorphic to C3. And what's the relation? Well, you have an equivalence class of a representation rho, and that has three coordinates, x, which is the trace of rho of x, y is the trace of rho of y, and z is the trace of rho of z. Now, in SL2, a matrix has the same trace as its inverse, so this is also the trace of rho of x, rho of y. Okay, so a pair of matrices is, a pair of matrices is determined up to conjugacy class, simultaneous conjugation by the trace of their traces and the trace of the product. So this can be regarded as an algebraic form of side, 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 or angle, angle, angle test of congruence in non-Euclidean geometry, either elliptic geometry or hyperbolic geometry. And so, now, what is the statement? What does this mean? So again, I'm looking at quotients of algebraic sets by algebraic actions. So this means every G invariant function regular function on hom pi G corresponds to a polynomial in these three variables. And in particular, if we're given an element in the fundamental group, something represented by a based loop or a closed oriented curve, then that means that its trace, which is conjugation invariant, will be given by some polynomial gamma in x, y, and z. So that means that there's some polynomial in the three variables evaluating the trace. In particular, gamma, taking gamma to be k, means that the trace of the commutator, I'll write this down, is equal to some polynomial in x, y, and z, and this can be seen to be this polynomial that I'm interested in talking about. And there's an analogous discussion for the four-hole sphere, which I won't get into, but it's quite fascinating. Okay. So that leads to studying this dynamical system of the automorphisms of this polynomial, just as in family of affine varieties. Okay. So the level, so I'll call this, that's k of x, y, and z. And so these are the level sets of k are the symplectic leaves of Poisson structure up here. The bivector field. Okay. Now, how might you get automorphisms of this polynomial? So we have this family of cubic surfaces in 3 space. Have this polynomial. So first of all, this is a symmetric polynomial. So the symmetric group on x, y, and z acts on the space. Also observe that if you change the signs of 2 of the variables and leave the third fixed, that preserves this simple polynomial. And so you get an action of the symmetric group S3, semi-direct product of Klein 4 group which you can think of as being plus or minus 1 squared. But this is actually isomorphic to the symmetric group on 4 elements. And there are certain natural 4-element subsets, which this is why I'd like to have the computer pictures to show you. But they're natural 4-element subsets for which these are the full automorphisms. And if you extend this affine cubic to a projective cubic, these will basically be the automorphisms of the projective cubic. But the character variety is an affine variety, and there are other automorphisms. In fact, there are infinitely many automorphisms because the whole mapping class group of the one-hole torus is acting. In particular, you have Dane twists around simple curves. So how might you get an automorphism, just very naively, of this cubic polynomial? Well, observe that this cubic polynomial, when you restrict to each coordinate line, is quadratic. And if you have one point on the curve, that's the solution of the quadratic equation. We want to find the other one. That's given by just the two roots summed to the coefficient of the linear term. Another way of saying that is that this cubic surface, the projection down, is a double branch cover, and this is just the deck transformation. So that's, but in particular, you get what have been called Vieta involutions. Say if you fix one of the coordinates, say x, let's fix y. I remember what I want to do. Okay. Let's say fix x and y, and then what can z go into? I'll call it z prime. That'll just be xy minus z. And then you have corresponding involutions for x and y. Okay, and so this describes what I'll call a free Coxeter group of rank 3, namely a free product of 3 groups of order 2. Okay, and so that, in particular, the Dane twist, so that as an automorphism of the fundamental group, the Dane twist around x is represented by this automorphism of the fundamental group. Probably getting it's a little bit wrong, but yx, then it's x inverse z. And then you can compute that the corresponding automorphism is very similar. The trace of x has to be fixed because x is fixed, but then z goes to y, and then this should go into right. So this will go to z prime. So that's one reason I want to use the one-hole torus, because it has a big mapping class group. It has these interior simple closed curves that you can do Dane twists around. You can't really do that for the 3-hole sphere or other surfaces that are in this homotopy type. Okay, so that's the next ingredient. So these exist when you have simple closed curves. What else do you have when you have simple closed curves? You have their trace functions, and they generate Hamiltonian flows. And these also can be thought of as twist flows in a similar way. We need to preserve the fundamental group, but you may have rho of x being rho flow along time t. That would be constant. Let's say rho t of y. Now that would be rho of y times something in the centralizer of rho of x centralizer. And then rho t of z would be the inverse rho of y. Okay, so these are the twist flows, and these were used in a paper of Lisa and Jonathan that I mentioned earlier, and then in the case of SU2, and in general, this, and I was interested in this because these things generalize the Fenchel-Nielsen twist flows that are used in defining Fenchel-Nielsen coordinates on the Fricka space of hyperbolic structures. And in particular, Scott Wolpert's work on the Weil-Peterson's symplectic structure was a motivation for my interest in this subject. Now, in the time remaining, let me describe what the level sets look like. This is what I have on the Mathematica program. So, and what we'll see are examples of both kinds of, both chaotic and trivial dynamics on the level sets. So let's start with k less than -2. It's easy to check that the critical values of k are plus or minus 2. So those are the places where the topology will bifurcate. K is less minus 2. Then the level sets, there are going to be 4 copies permuted by the sign changes. You can think of the sign changes as corresponding to spin structures. So these would be hyperbolic structures on the one-hole torus together with a spin structure. And these are given by homomorphisms into plus or minus 1. The mod 2 first cohomology of sigma. Okay. Now, remember, this is a statement. Vogt's theorem is so nice so that G here is SL2. But in doing hyperbolic geometry, we want to work with PSL2. That's a double cover. So the Teichmüller spaces or the Fricka spaces, each one of these is replicated 4 times. And we see this because the set of ends for asymptotically, each of these cubic surfaces will have 4 ends. The leading term is XYZ. So in the large, this looks like the union of 3 coordinate planes. And at infinity, we have a picture like this. And their 4 ends are here. So this is one of the 4 element subsets, which is exactly permuted by the S4. Okay. So that happens when you get down to the critical value -2, then these boundary components, the trace, it corresponds to the length of the boundary. And as the length goes to 0, the boundary component becomes a cusp, and we get the finite area surface. This is the famous Markov surface of Markov triples, where x squared plus y squared plus z squared equals xyz. Of course, you have 4 copies. That looks the same, but now the origin creeps in. That's solution. It's isolated in the real points, and it's a singular point in general. This corresponds to the 3 matrices of the Pauli spin matrices, the unit quaternions. 2 matrices of trace 0, and the product has trace 0. When k grows up, but from -2 to 2, remember these are the 2 critical values of k, then you still get pictures like this with 4 ends, each being a Teichmüller space. But now the funnel, the boundary component, when k is less than -2, the cusp when k equals -2 has now become a cone angle, and you get hyperbolic structures on a torus with 1 cone point, an isolated singularity whose cone angle is related to the trace. Okay, and the action is still proper on that, even though the representations are typically have dense image. So that's where this origin grows up to give a 2-sphere. Now this, maybe it's worth mentioning, here we have the first place where there's some chaotic dynamics. The action here is ergodic. The idea here is that the level sets of the coordinate functions, namely the orbits of the Hamiltonian flow, fill out, and in measure theory, measurable dynamics, we will ask for an invariant function, a function that's invariant under the Dane twist. The Dane twists are almost always going to be irrational rotations around these circular level sets. And that's one of the basic examples of an ergodic transformation. And so by using ergodic decomposition, we show that every invariant function under the Dane twist is under the discrete group, the Dane twist, is invariant under the Hamiltonian flow and therefore constant in that direction. Well, now that's to say that in the x direction, now you try it in the y direction, get the same result, and gradually you start eliminating variables, and it's nice to always be able to throw away sets of measure 0 to show that every function that's in almost everywhere invariant under the Dane twist will be almost everywhere constant. So here on this compact component, we have an ergodic, chaotic action, and we have proper actions out here. Now, we get to the next, okay, I better stop soon. You get, in the next step here, these 5 components touch, and you get a very interesting cubic surface that has 4 nodes. This is the Cayley cubic. These correspond to the reducible representations, and these are the ones that are the unstable points when you do the geometric invariant theory. You get a picture here. The action is ergodic on each of these components. That's actually a theorem in homogeneous dynamics going back to Calvin Moore follows from that. The interesting case now is when k is greater than 2 and the level sets are 4-hole spheres. Okay, again, we have 4 ends. And so the topology doesn't change anymore because these are the only critical values. So for now on, the topology is unchanged. It's always a 4-hole sphere, this action of this big discrete group, but the dynamics does. So when k is between 2 and 18, the action is ergodic. But something mysterious happens when k is equal to 18, because now there's an interesting point, -2, -2, -2. That corresponds to the representation of the 3-hole sphere, namely the finite area hyperbolic structure, the geometric structure, which has finite area and 3 cusps. And this is where, so the classical theory of cubic surfaces concentrates on the fact that cubic surfaces have 27 lines. 3 of the lines, in this case, all the lines are real. The three ideal lines, so you have 24 lines, but this is the intersection of 3 lines, and usually the lines don't intersect. But they're sometimes, and then when they do intersect, you get extra automorphisms. These are called Eckart points. Okay, and this is an example of the Eckart point, and I show that on this computer program, but I don't have time, but if anyone wants to see that. But that point, those 3 lines look like this, but then they open up when k is greater than 2. And I find this quite remarkable. Then you get hyperbolic structures, say on the intersection of this, where the curve corresponding to k I'm not even going to bother drawing it, but it's a curve that crosses itself 3 times. That's what K looks like on this surface here. That has fixed length, and you look at hyperbolic structures there. That's a wandering domain for the action. So here, it's like a Kleinian group where you have a region where there's very chaotic, interesting dynamics, and then regions where you have proper dynamics. And each of those regions have positive measure in this symplectic, this Poisson measure. So that's all I want to say. I hope I've conveyed some of the richness of this theory, of this dynamics on this Poisson manifold, and how it naturally arises in trying to develop a deformation theory of geometric structures. So thank you.